Today we're going to be explaining problem 2. This problem involves a pipe that is suspended equally from two forklift tines via a rigid strap. The pipe is momentarily at rest at the max angle, the strap mass is negligible, and the pipe has a center of mass at point G with a radius r. Using Newton's second law, force equals mass times acceleration, we know the forces in the free body diagram are equal to the mass multiplied by the acceleration, which is seen in the kinetic diagram. The required outputs that we need to find include the normal force on each tine, the required frictional force to prevent the strap from slipping, the angular acceleration of the pipe, and the max tension force in the strap. As the pipe and strap swing as one about point O, we can use the equations of motion for rotation about a fixed axis. Based on the pipe being considered a thin-walled pipe, the equation for the mass moment of inertia is mass times radius squared. We can also find this mass moment of inertia about a different point O using the parallel axis theorem. This is useful when we are deriving the kinetic energy. As gravity is the only force working on our body of mass, and gravity is a conservative force, then the conservation of energy equation applies. Deriving those equations for the required outputs gives the following summary. Now we will verify this with the use of MATLAB.
MATLAB has set some functions first to define the symbolic variables. And the variables are defined in the beginning of the script to allow changing of parameters. So the position, velocity, and acceleration of the pipe center of the mass is computed, which it then computes into a plot oscillation form. The oscillation actually tells us quite a lot of stuff, such as on the left-hand side of the oscillation, you can see the measurements for angular acceleration, angular velocity, and the angular displacement. On the right-hand side, you can see Newton's forces, which are the reaction forces at Rx and Ry. Analyze it to show that the displacement is at its max, and the pipe is therefore at the top of its swing. To further compare the values from the MATLAB angle, the displacement for the value must be set. So in our case, we've set 0.3941 radians, which gives us a time of 1.1889 seconds. As observed, you can see we've got very similar results. There's only probably a difference of like 2 newtons, 14 newtons between normal force and the required friction forces. And it's quite similar, which this goes to show that our results were quite precise in the simulation. And what does this tell us? So parameters within the Simulink file can also be altered to test different parts of the system, which is quite useful in everyday engineering tasks.